All right, so just remember, the final gonna be the last exam, and I'll this weekend I'm actually gonna be making the final, so I'll also make up a study guide. I'll do the same thing that I did for this study guide, where I'll tell you which topic it is, I'll tell you which chapter it's gonna be on, and I'll tell you which page to look on for those. So that way you know exactly what to cover, and that way you're not kind of blinded by like what's gonna be on the final. But you just kind of know for the final, since you're not going to be tested on chapter 10, it's going to be kind of highly focused on chapter 10. So it's not going to be evenly breaking down between all the topics. You should know that chapter 10, like that one should have a little bit more on the final because you haven't been tested on that on the test. All right. Any question in regard to that? All right, so let's get started with chapter 10. So chapter 10, we left off at 10.2. So let me go ahead and just transition over to the notes. All right, let me install a plugin. All right. So what we're going to work on today, we're going to work on 10.2. We probably should also get into 10.3. So for 10.2, we're going to be doing hypothesis tests for a population proportion. So just kind of remember, kind of like how we did confidence interval, where each section were a pretty much confidence interval. The only thing different is one section was for the mean, the other section was for proportion, the other section was for standard deviation. So just know for 10.2, 10.2, we're going to be focusing on the proportion. 10.3, we're going to be focusing on the mean. 10.4, we're going to be focusing on standard deviation. So you kind of want to make note on like the subtle differences between 10.2, 10.3, 10.4, because that way during a test or during a quiz, you should be able to decipher like, okay, are we testing the proportion? Are we testing the mean? Or are we testing standard deviation? All right, so let's go into the formula. So for the formula shouldn't be anything relatively new. These are formulas that we actually learned when we did chapter 8. So if you look at it, we have mu of p hat. Mu of p hat is equal to just p, the population proportion. We also have sigma p hat. Sigma p hat is equal to square root of p times 1 minus p divided by n. And lastly, to get the z value, you could just do p hat minus mu of p hat divided by sigma of p hat. So yes, no, p is the proportion claim. So what I mean by the proportion claim is pretty much what we're claiming the value to be. So we think that that proportion, like they're claiming that it should be that value, but we don't believe that that claim is correct. So when we talk about P is just a proportion claim. All right. So up next, we're gonna have, so we have 3 different null and alternate hypotheses. So here go one of the null and alternate hypothesis. Here you go a second of the null and alternate hypothesis. And lastly, here's the third null and alternate hypothesis. So if you look at the null hypotheses are all the same. It's saying P is equal to P naught. So it's saying there is no change. if you look at the alternate hypothesis, which is H1, it's saying P is not equal to P naught, or it's saying P is less than P naught, and it's also saying finally P is greater than P naught. So it's telling you the alternate hypothesis, that's where we're actually doing the claim. The null hypothesis, we're just assuming that the claim is correct. All right. Any question in regard to the null hypothesis or alternate hypothesis? All right, so let's go ahead and move on to a problem. Yeah, let's move on to a problem. All right. So up next, we're going to go over what is the p-value. So at the end, once we do the test statistic, you're going to find something called a p-value. So a p-value is something that we actually already found or something that we already did. The only thing is that instead of calling it something else, they're calling the p-value. So what we used to call it just the probability. So they'll tell us the probability of an event occurring is so-and-so. But now, since we're doing a hypothesis test, what we're going to do, we're going to call this the p-value. So what the p-value is telling us, it's telling you how likely is this event of occurring if the null hypothesis is true. So for this one, if you get a low p-value, that's kind of telling us that the null hypothesis might not be true. Because if you get a low p-value, the p-value is kind of saying this is very unlikely to occur given that the null hypothesis is true. So if you get a low p-value, you say there is evidence for the alternate hypothesis. But if you get a high p-value usually means that there's little evidence for the alternate hypothesis. So that's how we're going to use the p-value. So the p-value is kind of telling us if we have strong or if we have weak evidence. If the p-value is relatively small, we say we have strong evidence. If the p-value is large, pretty much we say we have little or weak evidence. Any questions so far for the p-value? All right. So in order for us to make a decision, we always usually want to check the p-value and compare that to our alpha. Because if you remember from 10.1, alpha is the probability of making a type 1 error. So if the probability of making a type 1 error or alpha is bigger than the p-value, that's kind of telling us that we have a small p-value. If it's the other way around, if alpha is bigger than p-value, if p-value is bigger than alpha, that's kind of telling us that we have little evidence. So if you look right here for the example, I put p is equal to 0.27, p is equal to 0.01. If p is equal to 0.27, that's kind of telling us this is very likely to occur. So that's kind of telling you that there's not a significant evidence against the null hypothesis. So if p is 0.27, that's kind of telling us that the null hypothesis is true. But if p is equal to 0.01, this is telling us that there's significant evidence against the null hypothesis. Because it's kind of telling us the likelihood that this would occur is such a low probability that the null hypothesis must be wrong. And then if you look in the bottom where it says rule of thumb, it says the rule of thumb is you reject the null hypothesis when p-value is less than or equal to alpha. You fail to reject the null hypothesis when p-value is greater than alpha. So this is going to be the rule of thumb that we use, and we're going to use this rule of thumb all for chapter 10. So anytime we have our p-value and our alpha, we always compare it. If your p-value is less than or equal to alpha, we will say reject the null hypothesis. If p-value is greater than alpha, we will say fail to reject the null hypothesis.
Will we always be given alpha?
You won't always be given alpha, but if alpha is ever not given, pretty much just assume alpha is equal to 0.05. All right. Any other questions? All right, so let's do this following problem. All right, so if you look at this question, it says alpha is equal to 0.10, p-value is equal to 0.27. So if you want, always put p-value first, then put alpha. So alpha they told us is 0.10, p-value they told us is 0.27. So which of these two values is bigger, my p-value or my alpha?
The p-value.
Yeah, p-value. So now if we look right here, this is the case where we fail to reject HO because p-value is bigger than alpha. So we'll say fail to reject HO. And we're done. Cool. Any question for that first example?
So wording is fail to reject, not accept HO.
Yeah, so for this one, we're kind of gonna go, because the thing is, the null hypothesis is already assumed to be correct. So we don't, if it's already assumed to be correct, we don't have to tell it that it's already correct. So we're gonna use fail to reject HO. All right, so let's do the second one. So the second one we have p-value is 0.001. We have alpha, which is 0.01. So what we want to do, we want to see which of these two is bigger. So which one's bigger, my p-value or my alpha? And if you want, you can also just put it in the chat. Perfect, alpha. So in this case, since alpha is bigger than p-value, now this is the case where you reject the null hypothesis. So when it comes to this, it should be something that's nice and easy as long as you either have the rule of thumb in front of you or you memorize the rule of thumb. Like this is something that should be nice and easy to calculate. There should be no kind of like hesitation. You have to just look at the two value and you see which of the two value is bigger. And depending on which of the two value is bigger, you're either going to reject the null hypothesis or you're going to fail to reject the null hypothesis. All right. Any question in regard to that so far? All right, so let's move on. And I think the problem should come up next. All right, so for this one, it's called fair die. So it said your friend claimed that he has a fair die, but want to bet on the number 6 with you. You suspect that his die is loaded and you decide to roll the die 200 times. 43 of the 200 rolls landed on 6. Testa claimed that the die is loaded to land on 6 at a significant level of 20%. All right. So let's go ahead and do this one. So if you look at the first one, it says check to see if the data is approximately normally distributed. So this is something you just got tested on. So if you remember, to check to see if the data set is normally distributed, which theorem should we check? Start with a C. Yeah, CLT, perfect. So you want to use the CLT. So for this one, since you're using the CLT, remember, we have two CLT. One of them is n is greater than or equal to 30. I'll call this A. Or we'll have n times p times 1 minus p has to be greater than or equal to 10. We'll call this B. which of these two should we use, A or B? Yeah, perfect, B. So you want to use B because if you look at this, this is proportional data set. If you notice, nowhere throughout the problem do they tell me this is my sample mean, this is a mean, this is the standard deviation. We're just given proportional data set. All right, so we're gonna check to see if I do n times p times 1 minus p, if that's greater than 10. So n, well, let me fill this out right here. N is equal to 200. So if we have a die, so here we go, it could land on 1, could land on 2, and we'll put 6 on top. What's the probability that the die will land on 6? If there is 6 sides? Yeah, 1 out of 6. So in this case, P is equal to 1 divided by 6. Everybody good so far? I got 200 is equal to n and P is equal to 1 over 6. All right, so I'm gonna go ahead and check the central limit there. So we're gonna say 200 times P, which is 1 over 6, times 1 minus P. And we're gonna see what does that give me. So right now what I'm gonna do, transition over to the TI-84. For that, we can see me work it out. So we'll say 200 times 1 divided by 6, multiply by 1 minus 1 divided by 6. All right, so you get 27.7 or 27.8, whatever you want to put. So if you look at it, we get 27.8, which if you compare that to 10, 27.8 is bigger than 10. So since 27.8 is bigger than 10, we could say that our distribution is approximately normally distributed. And that's it for checking that condition. Any question in regard to that condition? All right, so let's look at step 1. So in step 1, it says, in a sentence, describe the parameter that is being tested. So for this one, what we're testing the parameter that the proportion of time that a die will land on 6 is pretty much 1 divided by 6. So where are you gonna say that? So we put that. So the proportion of time that a die will land on 6. All right. So up next, we're gonna do the null hypothesis. So the null hypothesis, and we're also gonna do the alternate hypothesis. So for this one, the null hypothesis is stating whatever we used to believe about this die, we still believe it. So pretty much for the null hypothesis, we're gonna say the null hypothesis is that this die is a fair die. So we're gonna say P is equal to 1 divided by 6. So we're gonna say that the proportion of time this die land on 6 is the same as 1 out of 6 because it's the same as 1, 2, all the way through 6. So the alternate hypothesis where we're gonna put our claim, we're gonna put what we're thinking of. So P and 1 out of 6 will still be the same. But what do we think about the proportion that it will land on 6? Do we think it could be higher than 1 out of 6? Do we think it could be lower than 1 out of 6? Or do we think it'll be different? Yeah, good. So we actually just think it will be greater than this value. So we'll put P is greater than 1 out of 6. Any question on P greater than 1 out of 6? All right, so let's do step 3. So for step 3, it says find the value for n. We already found it to be 200, x, and p hat, and 1 divided by 6. Or p, sorry, not 1 divided by 6. So let's find x. So in this case scenario, since we're trying to find the proportion of time that this die landed on 6, x is how many times did it land on 6? So yeah, perfect. Don't even have to ask the question. So x will equal to 43. So then next what we're gonna do, we're gonna find p hat. If you forgot the formula for p hat, is x divided by n. So that means it's 43 divided by 200. So let me just do 43 divided by 200. Let me do it on my phone because I forgot my calculator. So it's 43 divided by 200. There you get 0.215. All right. So if you do 43 divided by 200, you get 0.215. Everybody good on 0.215? Okay, I'm also gonna do 1 divided by 6 just to kind of see how much of a difference do we have. So if you do 1 divided by 6, you get 0.16, and what do you say that's 7. Okay. So this are the two values we're kind of comparing. Because we kind of want to compare them, because if you look at it, we do have a difference, because 0.215 is different than 0.167, but we want to see if there's a significant difference. So we want to see if there's a significant difference between the two of them, because there is, like, if you kind of think about probability, we're not always going to get 0.167. That's like impossible that we're always going to get that value. Because sometimes we're going to go a little bit above that, a little bit below that, but it should be somewhere around that. So we want to see if 0.215, is that close enough to 0.167 for us to say that there's not that much of a difference. So that's what we're going to do when we're computing the test statistic and when we compute the p-value. Because the test statistic is to tell us how much of a difference do we have. And once we get to the p-value will tell us what is the likelihood we get 0.215 given that the null hypothesis is true. All right, but any question on what we did for step 3? All right, so let's do step 4. So for step 4, it says compute the following to get the test statistic. So if you look at it, it says compute mu p hat is equal to p, which we already know is equal to 1 divided by 6. And then if you look at it, it says compute sigma of p hat. So sigma p hat is going to equal to square root of p, which is 1 divided by 6, times 1 minus 1 divided by 6, all divided by n, which n in this case is 200. All right. Any questions so far? I substitute the value in. All right. So what I'm going to go ahead and do, I'm going to transition over to the TI-84, and I'm going to just show you how to enter this information in case you don't know. So first thing you want to do, you want to hit the second button and hit x squared. That will give you a radical. So then you go 1, 2. Actually, for this one, you might want to use parentheses. So we'll say parentheses 1 divided by 6 And then we'll use the other parenthesis and we'll say 1 minus 1 divided by 6. You do close parenthesis, and then we'll close this parenthesis too. And then you divide this by 200.
So should we be using, would you suggest the fraction or the converted decimal for this?
I would use a fraction. It kind of depends on you. If you use a converted decimal, you might want to use 4 decimal places. But you can also just use a fraction. I just like using the fraction because the fraction will give you a more of an accurate answer. Versus if you use a decimal, you are going to lose some precision, but not that much if you get like 4 decimal places.
Okay, thanks.
Yeah. Sweet. All right. Any question in regard to I got 0.026? All right. So standard error is 0.026, and we'll call it 4. So I'm going to use 0.0264 because the 5 in front of, well, behind the 3 is going to round up the 3 to a 4. So let's go to this. All right. So if you look right here, so P or mu P hat, we get 1 divided by 6. Sigma P hat, we get 0.0264. So let's kind of look at 0.0264. So the 0.064 is telling us that we should expect a standard deviation of 2.6%. So telling us as long, well, pretty much it's telling us like every time we do it, like we should expect a standard deviation of 2.64%. So now telling us we're always going to get 16.7%. And it's telling us that's pretty much going to be the standard deviation that we should be expecting. So we're not always going to be getting that value, but it should be somewhere close to that. Like if it go beyond that standard deviation or standard error, that's when you should kind of start getting worried. So lastly, what we're going to do, we're going to do the Z value. So the Z value, we're going to get P hat, where P hat is equal to 43 divided by 200. We're going to subtract that by mu of P hat, which is 1 divided by 6. And we're going to divide this by standard error, which is 0.0264. So this is going to give me my Z value. So it's going to tell me how many standard deviation are we from the mean. And if you kind of remember, like way back in chapter 3, we kind of went over like how many standard deviation or how many Z-score away from the mean we could be and still considered to be normal. If you remember that value that we use a value of 2. So if we're more than 2 standard deviation over, that's kind of telling you that this event is very unlikely to occur. But if we're less than 2 standard deviation, it kind of telling you that the event is more likely to occur. So right now what I'm going to do, I'm going to go ahead and find this Z value. So I'm going to go back to the TI-84, and we're going to just do this problem. So for the TI-84, first you want to use parentheses, 43 divided by 200. Subtract that by 1 divided by 6. And you divide all of this by the standard error, 0.0264. Press enter. And you get 1.83. All right. Everybody good with the 1.83? Cool. All right. So up next, we're gonna go ahead and do. We're gonna go ahead and find the p-value. So for this, for the chapter, I usually go over the p-value method and the classical method. But for this semester, we're gonna focus on the p-value method. So don't worry about the classical method, and don't worry about critical value. For any homework that asks you to solve for the critical value, just ignore it and just do the p-value method. So for the homework, any question that asks you to find the critical value or tell you to use the classical method, just ignore it and just do the p-value method. All right. So up next, we're gonna go ahead and we're gonna get this 1.83 and we're gonna convert it into a probability. So let's draw this out. So right now we're kind of gonna flash back and we're gonna flash back into what chapter this one should be? We're flashing back to chapter 7. So if you remember for chapter 7, once you find the z value, we standardize our data set. So we standardize our data set and now our mean becomes 0, standard deviation become 1. So that means right here we'll put 0. If you look at 1.83, 1.83 is this side over here because 1.83 should be bigger than 0. So then what we want to do, we want to decide which side of 1.83 do we want to shade. Do I want to shade the left side of 1.83 or do I want to shade the right side of 1.83? To be able to figure out which side to shade, what you want to do, you want to look at your alternate hypothesis. So let's look at our alternate hypothesis. If you look at the symbol that we use for our alternate hypothesis, we put greater than. So since we put greater than, that means you shade the right side. So when you shade the right side, this is what they call a right tilt test. So anytime you shade the right side is a right tilt test. Anytime you shade the left side is a left tilt test. And if you shade the left side and the right side, which is not equal to, that's called a two-tailed test. So for right now, we have a right tilt test. Any question in regard to how I shaded it to the right? Okay, so before, how were we able to find the probability once we had a z-score? What did we do next? It's a function in our calculator. Which function in our calculator did we use once we found a z value and we wanted to convert that into a probability? Start with there you go, normal CDF. So we want to use normal CDF. So for normal CDF, if you remember, the first thing you want the lower bound. So the lower bound, you have to look at your shaded area and you see what is the cutoff for the lower end. So if you look at the cutoff for the lower end, is 1.83. So we put 1.83 here. So then what we want to do, we want to look at the cutoff for the upper end. And remember, if there's no cutoff for the upper end or the lower end, you just put either negative infinity or positive infinity. So for this one, if you look at it, there's no cutoff for the right end. So what we're going to do, we're going to put 10 to the 10 power. Any question? I got 1.83 all the way to 10 to the 10 power. All right. So let me go ahead and transition over to the TI-84. For that way you can see how I enter it in case you've forgotten how to use normal CDF. So to use normal CDF, you hit the second button. You hit VARS. You go right here, number 2, where it says normal CDF. Remember, we never, ever, ever use normal PDF, only CDF. So for the lower bound, we'll put 1.83. For this one, we'll put 10 to the 10 power. And if you look at the mu, if you look at the sigma, it's already at 0 and 1. So you can just leave it as is, go to paste, go to enter, and you get 0.0336. All right, everybody good? I got 0.0336, and this is what we now call a p-value. So if you look at it, we're using the same method as before. The only thing different, instead of calling it, this is the probability of this event occurring, now we're just saying this is the p-value. So we're just using the same thing, but just giving it a different name. All right, any question for the 0.0336? All right, so let me transition over. All right, so if you look at step number 5, if you look at it, I selected the right tail test, so that means I want to fill out this one over here. So I put, this is the right tail test, so I checked that off, and then I put the probability of this right tail is 0.0336. So up and we're gonna get into the interpretation. So when I talk about the interpretation you telling me if I should reject the null hypothesis or if I should fail to reject the null hypothesis. So right here, we have the p-value. So right here, we put 0.0336. Alpha, if you remember our alpha back when we did this, we said significant level of 20%. So our alpha is 20%. Everybody give a p-value 0.0336 and alpha is 0.20. All right. So which of these two should I select? Should I select A or should I select B? Yeah, so for this one, if you look at it, p-value is smaller than alpha because 0.20 is 20%, 0.0336 is 3%. So 20% is definitely bigger than 3%. So for this one, you do want to check this one. So since I said p-value is smaller than alpha, what should I say? Should I reject the null hypothesis or should I fail to reject the null hypothesis? So we'll say this is A, this is B. Which one should I select? Yeah, so you want to say reject HO. So if I reject HO, you kind of have to go back to the null hypothesis and the alternate hypothesis. So when we say reject the null hypothesis, we're pretty much saying this is not true. So we're saying the null hypothesis is not true, and we're concluding the alternate hypothesis. So what that means, it means that the evidence that we have provided is enough to prove that the alternate hypothesis is correct. So what we want to do, we want to make a statement about that, pretty much just saying that the evidence has shown that there's a significant difference, and so on and so forth. So let's go ahead and do the interpretation. So for the interpretation, we'll say there is here significant evidence to support the claim that the all right. So that will be it for this interpretation. We'll say there is significant evidence to support the claim that the die land on 6 more often. And that's it. Any question in regard to this last prompt? All right. So I'm going to show you a shortcut way of how to do that, because pretty much that's how we would have done it before in chapter, what was that? Chapter 7 and 8. But the TI-84 actually had a cool function for this one. So let me go back here. Let me unerase this. So let me go ahead and transition to the TI-84. So on the TI-84, all you want to do, you want to go to stats. For this one, you want to go all the way over here where it says test, because we're going to start running a test. And then what we want to do, we want to go right here where it says number 5, where it says the one prop Z test. So let's go to one prop Z test. All right, so if you look at one prop Z test, it's gonna ask you for P naught, which is essentially putting the population proportion or the proportion claim. So we think that it should be 1 divided, so it should be 1 divided by 6. So that's the claim. Then what you want to do, you want to put the X value. So the X value in this case, we got it to be that it landed on 6 43 times. And then N was 200. And then if you look right here where it says prop is pretty much prompting you to enter the alternate hypothesis. So you want to either put that we said not equal to, less than, or greater than. So if you look at the alternate hypothesis, you should be able to see that we chose the symbol greater than. So we want to use greater than. And then what you want to do, go here, calculate. Okay. All right, so if you look right here, if you look where it says Z, it says Z 1.83, which is exactly what we got. If you look at the P, so right here, you do have to be careful because they have P and then they have P hat. Yes, no, P, that's the probability or the P value. P hat is the sample proportion. So P is equal to 0.0333, which is pretty much what we got. Well, we got 0.0336. So slightly a little bit off, but it's fine. And so if you look at this, this will give you pretty much the entire answer for you. So you kind of know what the Z and the P is giving you. All right, and that's how you deal with the calculator. Any question in regard to the calculator? And also the other kind of nice thing about this one, if you go right here and instead of going calculate, you could actually go to draw. And it'll draw the normal distribution and it'll draw the shaded area. And it'll tell you the Z value, which is right here, which is 1.8341. And it'll tell you the P value, which is 0.0333. All right. So if there's no further question, let's move back to the notes. All right. Any question for this first problem? All right, let's do some more. All right. So for this one said a researcher claimed that 16% of vegetarians are actually vegan. In a recent survey, 19 out of the 100 vegetarians stated they were vegan. Is there enough evidence at alpha level of 0.05 to support the claim? All right. So let's go ahead and see. So what are they testing? Or what are their claim? So what are they trying to claim here? Cool. So say, oops, 16% vegetarians are actually vegan. All right, so that's their claim. So they're claiming that 16% of vegetarian are actually vegan. So if you kind of look at that, that's kind of describing the null hypothesis, because the null hypothesis is always the one that has the equal sign. So for the null hypothesis, we're going to say P is equal to 16%, but we don't put 16%. We'll say 0.16. All right. Everybody good with the null hypothesis is P is equal to 0.16. All right, so let's put P, we'll put 0.16 here. All right. So what should be the alternate hypothesis? Because what they're trying to prove that 16% of vegetarians are actually vegan. So our alternate hypothesis, we kind of just want to disprove that. So which symbol should I use? The not equal sign, the less than, or the greater than?
Not equal?
Yeah, there you go. Not equal to. Because if we're trying to disprove that is not 16%, then we're going to say it's not equal to 16%. So it could be greater than 16%, which disprove it. It could be less than 16%, which also disprove it. So we could use either one of those. All right, so for this one, you want to put not equal to. So anytime they don't give you an indication if it should be greater than or less than, just always put not equal to. All right. Any question for the no or the alternate hypothesis? Sweet. All right, so for this one, what's my n value? Perfect, 100. What's the x? So of the 100 people, there you go, 19. All right, what's my p? So what's this? Well, if you remember for that one, it's just whatever they're claiming. So they're claiming that 0.16. So then p hat is equal to 19 divided by 100, which is 0.19. All right. Any question for step number 3? How I got n, x, p hat, or p? All right. So if you look at P, this person claiming it should be 16%, but when we found our sample proportion, we found it to be 19%. So what we want to do right now, we kind of want to prove that this difference, is this a significant difference? Because right now we have this 3%, but that 3% could have been by random chance. Because we could have a population proportion of 16%, but it could be that the sample that we got, that sample just had 19 out of the 100 were actually vegan. But what we want to do, we want to see, is that a significant difference? Because right now it is a difference, but we don't know it is a significant difference to say that it's not 16%. So let's go ahead and we're gonna find mu of p hat and sigma of p hat. So mu of p hat, well, this one easy, is 0.16. Sigma of p hat is gonna be equal to square root of p, where p is 0.16 times 1 minus 0.16, all divided by n, which is 100. So let me go ahead and calculate this in my calculator. So we're gonna go right here where it goes. Oops, not stats. So we're gonna go here, second, x squared, which is a square root. So we'll say 0.16 times 1 minus 0.16 divided by 100. And if we do that calculation, you get 0.0367. All right. Everybody good on the 0.0367? All right. And a little bit we'll actually do with the one probability test. I kind of just want to show you that, hey, we got this difference of 3%. But if you look at the standard deviation, or if you look at sigma p hat, it's telling us normally when we randomly sample, we get a standard deviation of 0.036. So kind of telling us we're not always going to get 16%, because based off of the sample that we're getting and based off of this population at 16%, by random luck, like it should deviate by 3.6% or 3.7%, however you want to round it. So the standard kind of telling us, or standard deviation kind of telling us that we're not always going to get 16%. And if we don't always get 16%, this is how much you're going to deviate from 16%. So up next, we're going to do, we're going to find the z value and we're going to find the p value by using the test function in CAS, well, not CAS, but the TI-84. So let's go back to the TI-84. So we're going to go to stats. We're going to go to tests. I'm going to do one prob z test. So number 5 again. All right. So for P naught, we're going to put 0.16. For X, X was 19. N was 100. And then if you look at the alternate hypothesis, we put not equal to. So you want to make sure that you select not equal to and go down here where it says calculate. Or actually, I don't want to do calculate. All right, so let's kind of get the main point. So if you look at the z value, we've got it to be 0.82. For this one, which type of test would this one be? Would this be a left tail test, a right tail test, or a two tail test? Yeah, two tail, perfect. And if you look at our z value, we got it to be 0.8183. If you look at our p value, we got it to be 0.81. 0.4132. Sweet. So if you kind of look at what the TI-84, the output that the TI-84 is giving you, it's kind of telling you that this could happen. So it's kind of telling you that we could get 19 out of 100 if our population proportion is 16%. So it's kind of telling you that this could occur um, given that the null hypothesis is true. So let's go ahead and switch back to my notes. All right. So a couple of new additions. So on part 4, I put the z value. I also selected that this is a two-toe test and that the p-value it gave me is 0.4132. Everybody go with that so far? All right. So I'm gonna go to step number 6. So step number 6, what we wanna do, I wanna select the p-value, which I already got it to be 0.4132, and I wanna get the alpha. So for the alpha, let's see. If you look at it, they tell us alpha is 0.05. All right, so we have p-value, which is equal to 0.4132. We have alpha, which is 0.05. So now what I want to do, I want to be able to say which of these two is bigger. So which one should I check off? Should I check off A or should I check off B? So should I say p-value is bigger or should I say alpha is bigger? Yeah, so for the most case, you do want to check off that p-value is bigger. So if p-value is bigger, what should I conclude? Should I reject the null hypothesis, so C, or should I fail to reject the null hypothesis, which is D? Yeah, good. So we failed to reject the null hypothesis. All right. Everybody get why we failed to reject the null hypothesis?
Good question. Oh, never mind. We're not using the classical method.
Yeah, we're not using the classical method. All right. Any other question before we move on to the interpretation? Okay, so let's go on to the interpretation. So remember, for the interpretation or for the conclusion, we always want to put the conclusion in reference of the alternative hypothesis. So in this case, the alternative hypothesis was that it was not equal to 6%. So for that one, we'll say, well, 16%, not 6%. We'll put there is not significant And that will be our conclusion for the second problem. And also just know on what you call this, on Canvas, there's like really no way to input all of this into Canvas. So you're not gonna have this layout, but you should use this layout to be able to kind of figure out what to input. So like just kind of know what do we call each one of these parts. Like say, this is p-value. This is test statistic. This one is pretty much just a conclusion. So you kind of know, like for the final, unfortunately, I'm not gonna be able to have this format because there's no way to enter this format into Canvas. So you just kind of know, like, what do we call each one of these parts? So that way, when I'm referring to that part, you kind of know what I'm referencing. All right, but any question in regards to this last problem? All right, so up next, we're gonna go ahead and do,
So
yeah.
when we use the one prop Z test, we don't need to do normal CDF because it gives us the p value.
Correct. So the one prop Z test is actually kind of like a nice one because it gave you the test statistic and it also gave you the p value. So you don't have to do that the normal CDF. I'll just kind of, well, for the first one, I kind of just wanted to show you like what we've been doing in chapter 7 and 8. Technically, we're still doing the same thing for chapter 10. The only thing different is we're just calling it a different name, but we're still doing the same thing. But yeah, just use the one probability test. All right, so let's go ahead and do this problem. So this problem is actually, I won't say the fun problem, but this problem is actually a true problem that actually occurred in real life. So if you want, you can actually look this up. So for this one, it says Kristen Gilbert was a nurse at a veterinary administration hospital in Northampton, Massachusetts. She had a reputation of being a particularly good in crisis. If a person went into cardiac arrest, she was often the first to notice something was wrong. Signal a code blue and administer an epinephrine. Often the patient's life was saved. Other nurses became suspicious both because of the number of cardiac arrests when Gilbert was on duty and also the number of deaths. Is there convincing evidence that the proportion of shifts with a death for a shift when Gilbert was working is greater than the overall hospital proportion of 0.045? What alpha should we use? What alpha should what alpha should be used? All right, so what this person had pretty much was a nurse, and pretty much what they're talking about, like when Gilbert or Kristen Gilbert was around, there's a lot of people going into cardiac arrest. When she's not around, there's not that many people going into cardiac arrest. So what we want to kind of prove is we want to prove like when Gilbert's around, the percentage actually go up of how many people die when they went to cardiac arrest. And when she's not around, like what the proportion of death when she's not around. So yeah, I think that's what the case was, the angel of death nurse. I'm not 100% sure, but yes, she might be the one. So first thing we're gonna do, we're gonna decide which alpha level we want. So I'm gonna give you 4 options. I know, super fun. So we're gonna say 0.01, 0.05, 0.10, and we're gonna do 0.20. So, all right, I'll guess I have to find the Jack the Ripper stats next. I'll try to find some. Okay, so for this one, what we want to do, we want to decide the alpha level. So if you kind of remember back when we did chapter 10.1, we went over what the alpha level is. The alpha level is the probability of making a type 1 error, which if you remember the case about guilty, not guilty, A type 1 error is the probability of sending an innocent person to jail. So for this one, what we want to do, we want to decide which of these 4 options should we use. So the smaller the alpha is, that means the more evidence we want to be able to convict this person. The higher the alpha is, the less evidence we want to be able to convict this person. So for this one, since we're trying to convict this person of killing these patients, which alpha level should we use? Should we use 0.01, 0.05, 0.10, or 0.20? So which alpha level should we use? Don't make me break out the Jeopardy music again. Cool. All right. So we'll say 0.01. Okay, cool. So we're using 0.01.
Where are you getting these numbers from?
I'm just giving you options.
Oh, okay.
Yeah.
I was looking for it in the question. I was like, I don't know where any of these answers are.
Oh, no. Those are pretty much because I wanted you to choose it. So that's why I didn't give you an alpha. I wanted you to kind of go like, okay, which of the alpha should we use of these 4 options?
Okay.
Yeah, sorry about that. Okay, so in a sentence to describe the parameter that is being tested. So what parameter is being tested? So the proportion of death when Gilbert can I put that? No. So we want to test the proportion of death when Gilbert is present. So that's our whole goal. All right, so for this one, if you look at the overall hospital proportion, what's the overall hospital proportion? Technically, you are correct, Amanda, but if you look right up here, they already gave us that value. So 0.045. So put P of 0.045. All right. So we're trying to prove when Gilbert is around, there's more people dying than the overall hospital. So which symbol should I use? Not equal to, less than, or greater than? Perfect. All right. Everybody good? My null hypothesis and my alternate hypothesis. Okay. So now we're going to want to use, we want to use a table. So we want to use N. So we want to use how many of the cardiac arrests would Gilbert present for? So if you look on the two-way table, here you go, death on shift. So either yes, somebody did die, or no, somebody didn't die. Right here says Gilbert present. So either she was present, which is a yes, or she wasn't present, which is a no. So for how many of the cardiac arrests was Gilbert present for? Or was she on duty for? Yeah, 256 per, well, 257, sorry. 257. So in those 257 cardiac arrests, how many of them actually died? Or how many of them were there a death during that shift? 40, perfect. So let's go ahead and find what p hat is equal to. So for this one, I'm actually gonna do it on my calculator. Unfortunately, I forgot my calculator, so I'm gonna use my cell phone. So we'll do 40 divided by 257. So you get 0.1556. All right. So when Kristen Gilbert is present and there's a cardiac arrest, 15% of those people who go to cardiac arrest, well, 50% of the shift that she's in, there's actually a death. So that's the percentage for Kristen Gilbert. If you remember, the overall hospital percentage was 0.045. So if you look at Kristen Gilbert percentage, and then if you look at the hospital percentage, like does it look like one is significantly bigger than the other one? Yeah, because if you look at it, there's pretty much 10% different. So that 10% difference seemed kind of a big one. Because if you kind of remember on the last one we got like a 3% difference. And then the one before that, I think we got like a 6% difference. This one, we get a 10% difference. So that's kind of telling you it's very unlikely that this could just happen by random chance. So what we're gonna go ahead and do, we're gonna go ahead and calculate some of this. So mu p hat is 0.045. Sigma p hat is 0.045 times 1 minus 0.045, all divided by n, which is 257. All right. So let me go ahead and use my TI-84 to calculate that. So we'll go second. 0.045. All right. So let's look at the standard deviation for this one. It's 0.0129. So it's telling us we should expect a standard deviation of 1%. But if you look at how much of a gap do we have from the p hat and p, we get a difference of approximately like 10%. So if we get a difference of 10%, and this is telling us we should have a standard deviation of 1%, that's kind of telling us we have a big gap. So when we do the test statistic, which we're now going to do, we should get a big z value, and we should be getting a small p value. So let's go to one prop z test. So for p naught, we're going to put 0.045. For x is going to be 40, n is going to be 257. For this one, we're going to change this back to greater than, and we're actually going to calculate this one. All right. So if you look at the z value, that's 8.55 or 8.56. So that's my test statistic or my z value. So it's telling us we're 8.56 standard deviation away from the mean. And the mean in this case is p, which is 0.05. So that's kind of telling us we have a huge gap. If you look at the p-value, so the first thing that should jump up at you, that you have 5.9. So you should kind of know that's impossible for you to have as a p-value unless this is in scientific notation, which if you look at the back end, it's telling you e to the negative 18. So that's telling you is in scientific notation. Because if you just put 5.9 as your answer, that will be considered wrong. because you can't have 5.9 as your p-value. It should always be a decimal between 0 and 1. So just know 5.9 is in scientific mode. So just be careful with that. So. Cool, perfect, Amanda. Oops, sorry. All right, so if you look at it, I enter my test statistic, which is 8.56. If you look at it, I selected this is the right tail test. The reason why the right tail test, because I'm putting the right side that is greater than. If you look right here, I have my p-value is extremely small. So you should kind of know, like, this is kind of giving us a lot of evidence to conclude that if the null hypothesis is not correct, we can't really say that the proportion of death when Kristen Gilbert is around and the number of deaths for the overall for the hospital, we can't say they're equal to each other. So we have to conclude the alternate hypothesis. Here, give me a minute. Something happened to my notability. All right, there you go. So you're kind of looking at it, this kind of supplying a lot of evidence. You say like the proportion of death when Kristen Gilbert shift is around, and for overall for the hospital, that's vastly different. So we should be saying there's a significant difference. So let's go down here. So for p-value, I can't fit all of those 0 here, so we're gonna say 0. For the alpha, we chose the alpha, which was 0.01. So which one should I select, A or B? So should I say p-value is smaller than alpha, or should I say p-value is bigger than alpha? Yeah, so let's try that again. Yeah, so we do want to say A, because alpha definitely bigger than 0.0000000, whatever it was. So alpha is bigger than p-value. So since alpha is bigger than p-value, what should I choose? Should I reject the null hypothesis, which is C, or should I fail to reject the null hypothesis, which is D? Yeah. So for this one, we'll say there you go. So we'll say there is enough, or being using significant. So there is significant evidence that she is, oh, why am I writing so horrible? Is guilty of murder. All right, and that's it. So we'll say there is significant evidence that she is guilty of murder. What a fun problem. All right, any question in regard to this last problem? All right, so the good thing about this chapter, not much is gonna change from 10.2, 10.3, 10.4. It's pretty much all going to be the same, where we're trying to see is there enough evidence or there's not enough evidence for the null or for the alternate hypothesis. So if you kind of understand the steps of why we're doing it, pretty much everything else should be nice and easy for you. So let's move on down.
So on these problems, we're getting kind of a good like path with each question in terms of where to go. But like on a test, obviously we won't have that. Should we kind of like copy these sets of questions to kind of have that format of how to progress through the problem? Does that make sense?
Yeah, because like when you're doing these type of problem, if you're using my format, you kind of want to just know, like, just use the format, but just know what everything means. So that way, like on the test, because like on the test, like where for step number two, it says state the known alternate hypothesis. Well, that should be pretty simple. But like for step number 4, I'm not going to be able to supply all of this for you. But like the keyword, if I ask you for the test statistic, I'm just asking you to give me this.
Perfect. Thanks.
Okay. All right. So what I want you to do, I want you to try to practice on this next problem. So I want you to go through all the steps. So finding the known alternate hypothesis, finding the test statistic, finding the p-value, and all the way to the conclusion. So try doing this problem. If you get stuck in any of the any of the parts, let me know, for that way I could assist you on anything. But do try to practice on this one, and do try to give it as much effort for this one. And that way, like once I go over, you can kind of see if you were on the right path, or are there still some stuff that you still need help with. I'll be right back. Keep on working on it. All right, so let's try working this out. So if you got stuck, hopefully I could show you why you got stuck and how to get you unstuck. If you were able to complete the problem, hopefully your answer matches up with my answer, so that way you know you understand this. So if you look at the problem, it says in 1997, 46% of Americans say they did not trust the media when it comes to reporting the news fully, accurately, and fairly. In a 2017 poll of 1,010 adults nationwide, 525 stated they did not trust the media. At the alpha 0.05 level significance, is there evidence to support the claim that the percentage of Americans that do not trust the media to report fully and accurately has increased since 1997? So in a sense, to describe the parameter that being tested, the proportion of American All right, so my screen have froze. So let me unshare and then I'm gonna reshare right now. For that way you can see what I actually just wrote instead of it being a blank screen. All right, so this is what you should have gotten. Well, it doesn't have to be exactly this as long as it hits some of the key things. So you do want to say proportion of Americans who did not trust the media. All right. So the null hypothesis will be P. And then if you look at it, the percentage of Americans who did not trust the media was 46%. So we'll say 0.46. So that'll be P is equal to 0.46. If you look at the alternative, we'll still put P, you still put 0.46, but since they want to prove it had increased, you want to put greater than. All right. Everybody good so far with that? All right. So if you look at your n value in this case was 1010. My x is 525. P hat is 525 divided by 1010. Let me go ahead and do that. So we'll say 525 divided by 1010. And you get 0.5198. So in 2017, that's the proportion of Americans who do not trust the media. So in 1997, the proportion was 0.46. So our whole goal is to see, is this a significant difference? So roughly, if you look at it, there's like a 5% difference. So we want to see if this is a significant difference. So let's go ahead and do part 4. So for part 4, you should have gotten 0.46%. Oops, sorry about that. For sigma p hat, you should get square root of p, which is 0.46, times 1 minus 0.46, all divided by n, which is 10. So if we do square root of 0.46 times 1 minus 0.46 divided by 10, here you get 0.0157. So if you look at the standard deviation is roughly 1.5% or 1.6%, and we have a gap of 5%. So that's kind of telling you that that gap of 5% is significant if the standard deviation is 1. But right now we're gonna go ahead and we're gonna do the one prop Z test. You have to kind of confirm that that difference is a significant difference. So we'll go to stats, we'll go to tests, we'll go one prop Z test. For P, we'll put 0.46. For X, you put 525. For N, you go 1010. And lastly, we want to put greater than, and you go to calculate. All right, so if you look at our Z value, we get a Z value of 3.81. So the 3.81 is kind of confirming our belief that that gap is a significant gap, because remember, kind of the rule of thumb, if it's more than 2 Z-scores away, it's significant. If it's less than 2 Z-scores away, it's not significant. All right, any question on how I got the Z value? If you look at the p-value, you should have selected that this is a right tilt test and that the p-value is 0.10007. So if you look at the p-value, they're given to you in scientific notation. So you want to convert that to standard notation and then work on that. Here, give me a minute. For some reason, it's not wanting to share. Share. All right, sorry about the delay, but we're back. So we got a Z value of 3.81. We got a P value, which is right here, because this is the right tail test of 0.00007. So they're kind of telling you there is a significant difference. So when we go right here to P value, I'm going to put practically that's 0. Alpha, if you look at our alpha level, they told us it's 0.05. So we'll put 0.05. So if you look at my alpha level, which is 0.05, if you look at my p-value, which is practically 0%, alpha is actually bigger, so you want to select the first one. Since alpha is actually bigger, we will say reject the null hypothesis. So for this one, as our interpretation of the result of the hypothesis test, we should put that there is significant difference between how many people trusted the media in 1997 to how many people trusted the media in 2017. And that's it for that last problem. Any question in regard to that last problem? All right, how do we feel about these problems? Did we feel okay about them? Great about them? Not okay about them? Yeah, and just like anything, like when the first time you learn it, like you need to practice on it. So you just go ahead and you start practicing on these type of problems. For that way you can get better and better on them because pretty much practice makes perfect. So you keep on practicing on them. Like the more you practice on it, the more you'll be able to kind of get the information from it. All right. So let's do 10.3. So for 10.3, what we're going to be doing, we're going to be doing hypothesis testing again. The only thing different, we're going to be doing hypothesis testing, but now we're going to be testing the mean. So for this one, you do kind of want to know the difference. So for this one, we're going to be doing population standard deviation is known. So in this case scenario, I have standard deviation of the population. So if you look at the null and alternate hypothesis, they're exactly the same as before. The only thing that's changed is the parameter. So instead of having p, we're replacing p with mu. So we're saying mu is equal to some sort of value. And then we're going to say mu is not equal to, less than, or greater than for the alternate hypothesis. All right. So those are my null, that's my alternate hypothesis. So this is the formula we're going to be using for the z-score, but we're really not going to be focusing on the z-score because in the calculator, there's actually a function that will do that for us. So if you look at it, it says x bar minus mu of naught, which is just the population claim of the mean divided by standard error, where standard error is equal to sigma divided by square root of n. So that's the formula we're going to be using for the first time, but we're pretty much just going to focus more on how to do it in the calculator. Any question in regard to that so far? All right, so let's scroll on down. All right, so we're going to do this one problem, and then that's going to be it for today. So for this one, said the board of a major credit card company required that the mean wait time for customer for service call is at most 3 minutes. To make sure that the mean wait time is not exceeding the requirement, an assignment manager tracked the wait time of 45 randomly selected calls. The mean wait time was calculated to be 3.4 minutes. Assume the population standard deviation is 1.45 minutes. Is there sufficient evidence to say that the mean wait time is longer than 3 minutes? Would a 2% significant level? All right. So if you look at what parameter are they describing and testing? So they want to test the mean wait time. So we want to test the mean wait time because we want to see if the mean wait time of their service call is actually 3 minutes. So we want to test that. So for the null hypothesis, we'll put mu is equal to mu something. So what are they claiming their mean wait time to be? Yeah, 3 minutes. So we'll put mu is equal to 3 minutes. Mu is equal to 3 minutes. So yeah, so they're claiming that their mean wait time is at most 3 minutes. So they're saying that's the longest you'll wait. But if you look at the last sentence, they don't believe that. They actually believe that it should be what? Well, they believe that it actually should be greater than 3 minutes. So for the alternative hypothesis, we'll say mu is greater than 3 minutes. Everybody good so far with mu is equal to 3 and mu is greater than 3. All right, so let's go ahead and find n. So if you look at n is 45 randomly selected calls. So n will be 45. If you look at x bar, we have to look at from that sample, what did they find that mean to be? So if you look right here, it says the mean wait time was calculated to be 3.4. And we already know mu is equal to 3 minutes. And then if you look at it, it says assuming the population standard deviation is 1.45. So that means sigma is 1.45. So far we have n is 45, x bar 3.4, mu is 3, and sigma is 1.45. Any question for any of those values? All right. So if you compare these two values, you could see that there's a difference. But what we want to do, we want to see, is there a significant difference? Because it could just happen that just those sample of 45, it could happen that it was greater than 3. But we want to see if the 0.4 is that's a significant difference for us to say that their claim is wrong, that their wait time is 3 minutes or less than 3 minutes. So that's what we're gonna go ahead and do. So we're gonna go ahead and find mu and sigma. So mu is equal to 3. Sigma of x bar will be equal to 1.45 divided by square root of 45. So let me go ahead and do that. So 1.45 divided by square root of 45. So you get 0.216. So that's our standard deviation. So that's how much variation we should be expecting. So if you look at the 0.4, there's a difference of 0.4, but this is telling us we should expect standard deviation of 0.216. So if you look at 0.4, that's kind of like a little bit less than 2 standard deviation away. But let's go ahead and find the z-score. So for the z-score, we're actually going to do this all on our TI-84. So we're going to turn it on. We're going to go to stats. We're going to go to tests. And we're going to do a z-test. So if you look at the z-test, what you first want to do, change it to stats, because we don't have the actual raw data. We have the stats. So for the mean, we put 3. For sigma is 1.45. For x bar, we got the sample mean to be 3.4. For n is 45. For this one, we want greater than. And let's just do draw. All right, so if you look at the z-score, we get it to be 1.85. We get a p-value for this right tail test to be 0.0321. All right. Everybody good how I got the Z value and how I got the P value? All right, so let me transition back to my notes. All right. So if you notice right here, I already put the P value, I already put alpha, I already put that this is a right tilt test, and I put that the P value is equal to 0.032. So all I have to do now is decide which one's bigger, P value or alpha. So which one's bigger, P value or alpha? So which one should I check off? Should I check off A or should I check off B?
Yeah. Three 0.216, 3.4, and is 45. And we think that it's going to be greater.
I put 9 chicken nuggets on my plate. 9 chicken.
Yeah, so we should choose B because that one is greater than, P value is greater than. Let me see, X1. So yeah, so you should choose B because P value is greater than alpha. All right, so if P value is greater than alpha, what should I say? Reject the null hypothesis or fail to reject the null hypothesis? Yeah, good. So you should fail to reject the null hypothesis. So if I fail to reject the null hypothesis, is there enough evidence or is there not enough evidence? So should I say there is significant difference or should I say there's not significant difference? Yeah, so I'll say there is not significant difference. Not significant. Oh, yeah. Evidence to wait. So we'll put there. That is. So that should be there. So put there is not significant evidence to support the claim that the mean wait time is greater than 3 minutes. And that's it for that last problem. So if you kind of notice this problem and the last problem or the last section is pretty much the same. The only thing different, we're testing out different parameters. All right, but any question for this last problem? And also, kind of going back to this one. So when we do the z-test, for sigma, you always put the sigma, the original sigma, because the reason why is asking us for the sample size, because if it's asking us for the sample size, it's automatically going to calculate sigma x bar for us, because it's going to do 1.45 divided by square root of 45. So for sigma right here, you always want to put the original sigma. You don't want to use the sigma that you calculate by doing sigma divided by square root of n, because that's why the calculator is asking you for the n value, because it's going to do that calculation for you. So there's no need for you to enter the value that we got. All right, but any question in regard to this last prompt? All right, so we're gonna just stop here for today, and that way we'll continue on with this on Wednesday. So if you have any questions, remember I do have office hour right now, so I'll have office hour from right now all the way to 12:15. So if you do have any question about anything, if you have question about the test, if you have question about this section that we went over, you could ask away, for that way I could help you out with that. But that's pretty much it for today's lecture. Any question before I shut this down and go to my office hours? All right. So that's it for today. Have a great day, and I'll see you Wednesday. So stop share and